Balanced trees solve a very specific problem that we have in the regular trees. So as we go through this sequence of videos, like before, I'm not trying to teach you the algorithm. The algorithm's in the book, it's online, it's a lot of different places. I want to teach you the concepts behind the algorithm so it helps you debug and understand what your algorithm is trying to do, and you can talk intelligently about it if somebody comes and asks you. So the foundational need for balanced trees is the fault in the simple rules of the binary search tree. So if I add items to a binary search tree in order, 1, 2, 3, 4, 5, notice they're all to the right. The logarithmic benefit of being able to search half of the size space at any given time or less is thrown out the window because now essentially it's a linked list. It's search order n. The number of items is the potential I could be searching. So it comes to the question, hey, how do I balance it? And then what does that mean? So there's one important concept I want to get past right away. You might have the idea that a balanced tree is just simply I count the number of nodes to the left, I count the number of nodes to the right, and as long as they're equal, we're happy. That is absolutely not the goal of at least the red-black search algorithm. You could write an algorithm, and you might see algorithms out there that do that, but that's not the goal. We don't need perfect symmetry all the time because we get close enough to the search space without perfect symmetry. We can definitely have something that's technically unbalanced as far as numerical count goes, but is pretty good as far as the search count goes. Because remember, each row contains many values, and one left-hand branch could be totally filled, and the right-hand branch could be almost empty, but they're still the same search time. All right, so let's talk about this concepts. Now, the book we're using has a way of talking about it in the notion of a 2-3 strategy tree. The 2-3 strategy tree basically gives you this concept that I can put two values into a single node. Now, it's kind of weird, but if once we allow a single node to have two values conceptually, not practically, we'll get to the implementation later, but conceptually, that means I now have everything to the right is greater, everything to the left is less, but I have this notion of what are the items in between. So, A is less than L, Z is greater than Q, but there are values L, M, N, O, and P that live between these two, that we can store them essentially between them. So instead of having a left and a right, I conceptually have a left, right, and middle. So when I go and add to any given node, again, conceptually, I can not just simply add to the left or right, I can add between them. So let's say I've done that, and now I have an L in between. Well, in theory, I could have a 4 node, 3, 4 here. So I have three values, D, L, and Q, which then have everything less than D, everything greater than Q, and then the two other nodes to in between. So between D and L and between L and Q. And so adding a D to that node would make this 4 node value, but we don't like the 4 node value. That's too complex. We like the simple structures we had before, at most with the concept of in between. So what we can do in this case is we can restructure what would be a 4 node value into a 3 node value. So we put the L in the middle, the D to the left, the Q to the right, we're back to where we started. But now we have 3 nodes in theory that I can each have 2 values. So this algorithm conceptually gives you temporarily moments in time where I go from our nice clean 2 values, potentially, the 2-3 strategy into this 4 node, but then we immediately correct that back into something that we're more familiar to seeing. So we split that back into the more traditional single nodes that we're used to seeing. All right, this concept is really useful because it allows our balancing algorithm to essentially work and insert into trees pretty simply. So when we insert in any given node by making it into a 4 and then balancing it, it allows us to deal with our trees. So when we add to a tree, like let's say we're going to add the value O to this tree. Well, the first thing we want to do is find where the value goes inside of the tree. So O is greater than L, so we go to the right. It's less than Q, we go to the left. And then we can add an O here to the solo node and make it a double node. And that's fine. We're okay with this. That's all we need to do. There's no other work that needs to happen. We're happy with that. So since we have this happy one, we're good to go. But let's look at another example. Let's say instead we're going to add in the a B inside of here. Oops, there's a little typo right there. But there's a B makes this into ABC, that 4 node, instead. All right. So what I do then is I'm going to correct that by bubbling up the middle. So if you notice, I took the B here, I kept A and C, and I bubbled the middle up to make this one now a 4 node instead. Now, if this wasn't a 4 node, if there's a 2 node, it'd be fine. You could just keep it, the way it was. But now, since this is a 4 node, I need to address it again. So again, I'm going to split the middle node here, and then I'm going to bubble up the middle being in between L and A and C. I'm going to split this node. I'm going to take the middle value D, and it's going to bubble up to L. And so I'm going to roll that one up again. And then you notice I split B and F, and they become more traditional tree structures that we're used to seeing. And then we have D and L up top as this double node. So we just continue to roll the middle value up until we get to the top. And then if we happen to get to the top and there's a 4 node up there, then we split that one as well. And we basically everything just at that point gets 1 level deeper. We increase the height of it by 1. So the question is, do you have to rebuild your entire tree structure now that we've introduced this notion of the 2-3 nodes as opposed to the binary node we had before? Yes and no. So no, we're not going to actually build code that has a left, a right, and a middle node. We're not going to be swapping the data structures that way. What we're going to use is we're going to use a property to say whether or not the traditional 2 structure represents a 2 node or a 3 node example. And so that is where the red-black notion comes into it. Instead of actually having 2 data types and switching back and forth the types of nodes, which you could do, the forebears that have written data structures before us came up with this really clever strategy of just essentially using either a Boolean flag or a single value that just says red or black. And that red or black flag represents the patterns that we just saw. Are we looking at a 2 node structure or a 3 node structure, or what are we seeing? So this first section that we're talking about is conceptual, and what you're going to code looks different. But understanding this concept is going to help you understand why we use this red-black structure. That essentially, when we're talking about a red node, it's going to be flagging in whether we have these extra situations, and black nodes are going to be kind of happy with the traditional tree structures. And so as we see those things flip back and forth, we'll know, is the tree balanced or not, or do we need to take action? And that's going to be the important thing in our algorithm. So let's leave that for a second, and we'll come back and we'll play with it next time, introducing the idea of red-black trees as the way of actually writing code.